Organizer is very loud in this room for some reason. All right. All righty. So geothermal. Let's talk about geothermal. This is kind of an interesting topic. This particular lecture on why the Earth is actually hot. Before we continue, my recommended text for this, excuse me, for this unit is this book by Stover and Booker, which is available from the library website, and I'll use some stuff from it over the course of this unit. Okay, and so the motivation behind using geothermal energy is that if you look at the equivalent CO2 emissions from various forms of energy used for power generation, there's a pretty wide range. Coal is the most carbon intensive, about 1,230 grams equivalent per kilowatt hour. Natural gas is much less carbon intensive, but still produces CO2. But there are some very low carbon intensity forms of generating electricity, which include geothermal and nuclear, as well as some other ones. And so, rather than trying to capture the CO2 that's being emitted from burning coal or natural gas, how about just don't produce as much of it to begin with? So you can look at, either lower temperature geothermal, which requires some additional energy input, or something like enhanced geothermal, which is very hot and produces fluids that are hot enough to directly generate steam themselves. And so that's the motivation. That's what we'll talk about, how all this works. Okay, the reason that geothermal energy works is because the Earth is hot. And if you look at a cross-section of the Earth is divided up into a number of different layers. At the very middle, there's the inner core, which is actually solid. It's mainly composed of nickel and iron. It's very hot down there. It's surrounded by the outer core, which is liquid. And then there's the mantle, which is about almost 3,000 kilometers thick. And then the very, very top section there is what we call the lithosphere, which is the portion of the Earth that deforms in a brittle manner. So you have faults and fractures and stuff. And the asthenosphere, which is most but not all of the mantle, deforms ductily. So it actually flows by creep. And as we'll see, that's actually an important process. This is what the temperature profile looks like from the surface down to the middle of the Earth. The inner core is about 5,000 degrees Celsius, very hot. And the process of getting that heat out from the middle of the Earth to the surface is what drives geothermal energy. It's hot. The deeper you go, the hotter it gets. And so you might ask, why is it so hot? Well, there's really two sources of heat. One is that, here we are 4.2-ish billion years after the Earth accreted, it formed. There's still leftover heat from that process. And there's also kind of a minor contribution from the decay of radioactive elements. This is often cited as the main reason why the center of the Earth is hot, and it's actually not. If you look at, this is a nice modeling paper from 15 years ago now, but they're looking at heat flux from the different radioactive elements and their contribution to the heat flux from the Earth. Now you can see the main ones are potassium, uranium, and thorium. And the relative contributions have changed over Earth's history because they decay at different rates. And so at different periods in time, there were differing amounts of these elements. So right now, today, if you look at the relative contribution from them, thorium is actually the major contributor in terms of radioactive heat, whereas early on in Earth's history, it was actually potassium. So there's just differences in how that works. But today, you can see that the heat flux from radioactive decay is something on the order of 20-something terawatts. And as we'll see, that is less of a contributor to the overall thermal structure than you might expect. So there's two ways of transferring heat. So I told you that the heat coming from the middle of the Earth is trying to get out to the surface, and that's what's driving geothermal energy. And so you can transfer heat in two ways. You can either do it by conduction, which is just heat moving from something that's hot to something that's cold. And then there's convection, which is if you have a substance that's moving like a fluid, the heat will be carried along with it. Okay, so we'll keep those two things in mind here. And so the other thing that we have to keep in mind is that if we think of the Earth as a solid body, the temperature is not the same everywhere within that solid body. So it varies with position. It also is going to vary with time because the heat is gradually dissipating out into outer space. And so we can describe the thermal structure of the Earth using the convection diffusion equation, which describes variations of temperature in space and time. And in 3 dimensions, in its vector form, it looks like this. So capital T is the temperature. This kappa is a term called thermal diffusivity. And then the V is a velocity field for any components of the Earth that are moving. And then this is the partial derivative with respect to time. So this should tell us that the change in temperature with time of a particular point in the Earth depends on the local temperature gradient and also the velocity with which that particular point is moving with respect to the rest of the Earth. Okay, so some of you may have heard this story, but it's an interesting one. So there was this guy named William Thomson, better known as Lord Kelvin, and he and Charles Darwin got into a fight over how rapidly geologic processes happen. I think they were talking about some type of an erosional process of a chalk formation. So this was back in 1864, and Kelvin said, "You know what, Charles? I'm going to show you how old the Earth is." And he, came up with an estimate for the age of the Earth based on what they knew at the time. Now, at the time, they knew that the temperature of the Earth increases with depth. They observed this in the United Kingdom and coal mines, and it was known in other parts of the world as well. And so he said, "Okay, look. If it's hotter at the center of the Earth, I can use what we know about the present day geothermal gradient to estimate how long it would have taken that thermal profile to evolve by conductive heat transfer." Okay, so Kelvin assumed the whole Earth is solid rock, heat transfer is only conductive, and the maximum temperature at the center of the Earth cannot exceed the melting temperature of rock. So there's your boundary condition. Okay. So if you go back to the convection diffusion equation, you can make some manipulations here. So we're only assuming conductive heat transfer. That means that this velocity vector is 0, so we can ignore that term altogether. Let's assume that the diffusivity is constant, so we can take it out of the divergence operator here, and this simply becomes the Laplacian of the temperature field. And then if we're only working in 1 dimension, which is okay for a homogeneous spherical body like the assumed the Earth was, you can just use 1 spatial dimension. So you end up with this equation here, and the negative sign again is because we assume that depth increases as we move down. Okay, and so you can solve this equation. If you put an initial condition that the whole Earth was at the melting temperature of rock, which we can't exceed, and then the boundary condition is that the surface temperature is very, very much smaller than the initial temperature. So let's make it approximately 0. And so if we're looking at the difference in the temperature between the present day and the initial temperature, you can write this equation here, for the temperature as a function of depth and time. And it's this integral here can be expressed as this error function. So this is kind of your classic solution to the diffusion equation. If you haven't seen this already, you probably will sometime soon. So that's how you come up with that solution. Okay, now the geothermal gradient, which is how quickly temperature changes with depth, they had some understanding of that in the mid-1860s. So if we take the first derivative of the error function, it actually has a closed form solution that looks like this. And so the geothermal gradient as a function of time is simply going to be the derivative of temperature with respect to depth at depth 0, so at the surface of the Earth. And you can go through the manipulation here and plug in the numbers, and you see that this is what the geothermal gradient would be after a certain amount of time, with the understanding that the interior of the Earth is still hot, but is cooling down gradually. And so you can solve this for time, and you can see that if you measure a particular geothermal gradient, if you started at some initial temperature, then it would have taken an amount of time equal to T to get to that geothermal gradient. So now all we need to do is figure out what the present day geothermal gradient is, make some reasonable assumption about the thermal diffusivity of the Earth, and we'll get the age of the Earth. That's all there is to it. So Kelvin looked up ranges of geothermal gradients, and they were anywhere between 1 degree Fahrenheit per 110 feet and 1 degree Fahrenheit per 15 feet. It's kind of a wide range. He said, okay, let's split the difference. We'll make it 1 degree Fahrenheit per every 50 feet, which works out to about 36 degrees Celsius per kilometer. He assumed an initial temperature of 7,000 degrees Fahrenheit. Now, this is a little kind of a weird point. So I went back and I read his original paper from 1863, where he lays this stuff out. And he just said, you know, that it's much higher than the melting point of either granite or basalt. And I don't know how he came up with it. He just says temperature is, it's what it's generally assumed to be, the melting point of rock. He just throws that out there. So I don't know. To this day, it's still a mystery. They knew experimentally that most rocks have a thermal diffusivity around order of 10 to the minus 6 meters squared per second. So he plugged all those numbers in here, and he came up with an age of the Earth equal to 99 million years. And he said, boom, Charles Darwin, you're wrong. 99 million years it is. Okay. So obviously, well, actually not necessarily obviously, but we now know that this is completely wrong, like way wrong. He's way off. So the question is, what did he get wrong? Okay. And so there's a famous story. So Ernest Rutherford was one of the early workers on radioactivity. And he said, you know what, I think what Kelvin got wrong was that he failed to account for radioactive elements. Because, you know, as we saw previously, those do contribute some heat. And so there's a famous story where Rutherford was giving a lecture and Kelvin was there. He was at that point, it was 1904. Kelvin was a very old man. And Rutherford didn't want to piss him off by saying that he was wrong. And so he was like, how am I gonna say this without sounding mean? And so he said, okay, so here's the thing. They didn't know about radioactive decay back in those days. So, you know, Kelvin, he was just acting off of what they knew. And he said, he limited the age of the Earth, provided no source of heat was discovered. And look, I discovered a new source of heat. So it's okay, Lord Kelvin, you're fine. That's, you know, generally taken to be the story of what Kelvin got wrong, okay? But that's not actually it, okay? If we look at numerical models, if you ignore, you know, if we, you know, knowing what we know about heat transfer in the Earth today, if you ignore radioactive decay, it really doesn't make a difference, okay? So let's, here's another graph. This is from a modeling study. So this is present day, or present day is over here somewhere, looking at time since the formation of the Earth. And so you can look at the heat flux. This is in milliwatts per square meter. You can see that including radioactive decay, you know, makes more of a difference today. But back in the early stages of the Earth, it made only a small contribution. So that's not really the reason that Kelvin got the age of the Earth wrong. It really had to do with the fact that he assumed that heat transfer was only conductive. Okay, and it turns out that one of his former assistants figured out what was wrong here. So the problem is that the mantle actually convects. It's like a boiling pot of water. I told you that it deforms ductily. And so that convection moves hot stuff up to the base of the crust, and then it cools off, and then it sinks back down again. And so this process is always ongoing. And so this matters now because we go back to the convection diffusion equation. Now we have a non-zero velocity. And so if we simply assume a constant velocity, it doesn't really matter what it is, and working in one dimension, now we see that if we add this velocity term over here, it means it counteracts the conduction term here. And so it means that the temperature of the Earth will cool less rapidly because of that convective heat transfer. So if you include convection, you'll get an older estimate for the Earth. And so what Perry did was he said, okay, let's assume that the Earth has a very thin solid crust, which has some heat flux across it. We have to assume a thickness of the crust. We'll assume that the interior temperature is much higher than the external temperature. And so we can just write this like this, where this Ti is the interior temperature. So now we're just looking at the heat transfer across the crust, okay? So we can figure out the total heat loss. That's just going to be heat flow multiplied by the surface area of the Earth. So that's what that is. And that's got to be balanced by the cooling rate. So we're losing heat at a certain rate, and that's going to equate to loss of energy of the interior. So here's the heat flow. So that goes on the left side here. And then the loss of energy of the interior on the right-hand side here, if everything's at equilibrium. And so you can simplify this and come up with an easily solvable differential equation where we get the solution here. So the natural log of the initial temperature of the interior temperature is given by this term over here. And we have constants of integration. And so if we specify boundary conditions where we have an initial temperature at T0, this all works out. We figure out what the constant is. And then we see that the initial temperature is given by, or the instantaneous internal temperature looks like this. And then the geothermal gradient is simply going to be temperature difference across the crust. And we end up with this expression here. So this looks a lot different than what Kelvin came up with. But if we solve for T and then plug in some values for what we know the constants in here to be, the thickness of the crust, Earth's radius, density, specific heat, thermal conductivity, molten basalt temperature, typical geothermal gradient, we get a time of about 2.5 billion years. So that's much closer. Now we know from radiometric dating that it's about 4.5 billion years. But this really is the reason that Kelvin got his age of the Earth estimate wrong. It's because he failed to account for convection. It had little to do with radioactivity. And that has a lot to do with how we get this thermal profile through the Earth. You'll notice that the thermal gradient is not very large throughout the mantle and outer core. That's because they both convect. That's a very efficient way of transporting heat. But you have a very strong geothermal gradient in the crust. And that is that heat being transported up near the surface. And that's what we extract for geothermal energy. It gives rise to the whole thing. Okay. And, you know, the reality is that the heat flow at the surface of the Earth, it varies a lot depending on where you are because of the dynamics of mantle convection, which is related to plate tectonics. But there are certain spots where you have very hot rocks very close to the surface. And that's what we'll be talking about in the coming lectures. Okay, well, thank you all for coming. I hope you all have a good weekend, and I'll see you back here Monday.